Hello and welcome. Today we'll be looking at another example on points of contraflexure. So we'll be solving the above question. Here we have a moment here which is 282.5 kilonewton meter. While at the other end there we also have another moment which is 417.5 kilonewton meter. A uniform distributed load with 7.5 kilonewton meter and a point load of 120 kilonewton, and then you can see clearly the distance from B to D is 10 meter, C to D is 5 meter, C to A is also 5 meter. So for us to solve this question, we are going to be starting with the summation of the vertical forces, summing them to be equals to 0, and then taking our upward force to be positive and our downward force to be negative. All right, so sum of upward force will be equals to summation of downward force, and the upward force is here is the reaction at A and then the reaction at B. So upward force, which is reaction at A plus reaction at B, will be equals to 120 plus we have a uniform distributed load here which we are going to convert to a point load. How do we convert uniform distributed load to a point load? We are going to multiply the weight of the uniform distributed load by the total distance it covers. You can see it is sitting on point D and what B, and which is 10 meters. So we are going to multiply 7.5 by 7.5 multiply by 10. So it means that reaction at A plus reaction at B will be equals to, so if we add 7.5 times 10 is 75. 75 plus 120 is nothing but what? It's nothing but 195. So we are going to have 195 here. So let's call this our equation 1. So the next thing we are going to do is to take the summation of moment about point A to be equals to 0. All right, you are going to need to listen carefully here. Here we have said that our upward force should be positive and our downward force should be negative. It means that the moment produced by our upward force, if you look at this, you are going to observe carefully that our upward force is giving us an anti-clockwise moment. That is a moment which is the same as this moment here. You can see this one too is also an anti-clockwise moment. So it means the moment produced by this upward force will be positive, and this anti-clockwise moment will be positive, while our downward force is going to be giving us a what? A clockwise moment, which is going in the same direction with the moment. Yeah, so while this one is positive, this other and this moment is positive, this moment here will be negative, and the downward force is here to be negative. So let's take our moment in respect to what? Point A. So we'll be starting with the reaction at B. So we are going to have reaction at B multiplied by the total distance, which is 20, plus this moment that is here, which is 417.5, which will be equals to, so our downward force, we have 120 multiplied by the total distance here, 120 times 5 plus, and we are going to have 7.5 times 10. You know, we have a point load here, which is when we convert that to a point load, we have it towards 7.5 times 10, which is what? 75. So we are going to have 75 here multiplied by the total distance. So how do we know the distance that it covers? So we are taking our moment about point A. Don't forget, when we convert uniform distributed load to a point load, it's going to act at what? Half of the distance. So half of 10 is 5. So 5 plus 5 plus 5 is going to give us what? 15. So we are going to have 15 here, plus the moment that we have at this side, which is 282.5. All right, so here we are going to have 20 RB plus 414.5, which will be equals to 120 multiplied by 5 is going to give us what? 600, plus 75 multiplied by 15, that is 1125, plus 282.5. All right, so we are going to have 20 ROB here plus 417.5, which will be equals to, if we sum all of this stuff together here, we are going to have 20075. All right, so that is what we are going to have. All right, so the next thing is we are going to collect the like terms. That is 20 ROB will be equals to 20075 minus 417.5. all right, so 20 ROB, if we subtract that, we are going to have 1590 here. So for us to get ROB, we divide both sides by 20. All right, so now our reaction at B will be equals to 1590 divided by 20 is going to give us 79.5. So we're going to have 79.5 kilonewton. All right, so for us to get our reaction at A, we are going to subtract 195 from what? Reaction at B. So 195 minus 79.5. We are going to have our reaction at A to be equals to 115.5. 115.5 kilonewton. All right, so that is what we are going to have. So the next thing we are going to be doing is we are going to be doing our shear force calculation. All right, so we will be starting with the shear force at point B. So shear force at point B will be equals to, so at point B to our right hand side, we have an upward force, which is reaction at B, and then we have said the upward force should be what? Positive. So our reaction at point B is going to be 79.5 kilonewton. All right, that is the shear force. So let's go for the shear force at point D. All right, the shear force at point D. Don't forget, we start at point D here. We are going to have a this upward force and a uniform distributed load. That is, we are going to have 79.5 minus, because we have a uniform distributed load which we have converted to a point load, and if we do that, we are going to have it to be what? 75. So by the time you subtract 75 from 79.5, you are going to have nothing but what? 4.5. We are going to have 4.5 kilonewton. All right, so we are going to have 4.5 kilonewton. All right, so that's what we are going to have. So the next one is the shear force at point C. All right, the shear force at point C. You start at point C. Don't forget we are having this upward force, uniform distributed load, which is going to become, which we convert to a point load, and this downward force here. So we have dealt with these two, which is when we resolve them, we have 4.5. So don't forget we have a downward force, so which is going to be minus 120. So by the time you subtract 4.5 from 120, you are going to be having minus 115.5 kilonewton. All right, so the last but not the least, which is the shear force at point A. All right, the shear force at point A. Don't forget, we already have, when we start at point A, we are going to be having upward force, uniform distributed load, and this downward force here. We have resolved these three, which is giving us minus 115.5 kilonewton. All right, so here at point A, we now have a upward force, which is reaction at B, which is going to be plus 115.5. So if we sum this together, you are going to have 0 kilonewton. All right, so the next thing we are going to be doing is we are going to be calculating, doing our bending moment calculation. All right, so the first one is the bending moment at point B. All right, so bending moment at point B. All right, so don't forget at point B, we have this moment that is here, right? So we have this moment that is here. And don't forget, we said our upward force is what? Positive. And our outward force is giving us a what? Anti-clockwise moment. So it means our anti-clockwise moment will also be what? Positive. So this moment here is a clockwise moment. So it's going to be what? Negative. So we are going to have negative 2825.5 kilonewton meter. All right, so that is it. All right, so the next thing we are going to consider is the bend moment at point D. All right, so the bending moment at point D will be equals to, all right, so now if we start at point D, we have our upward force, which is arrow B multiplied by what? 10. Our upward force is positive, so arrow D here is going to be 79.5. 79.5 multiplied by 10 minus our downward forces here. Our downward force here is going to be the uniform distributed load here converted to a point load, and when we convert that to a point load, 7.5 times 10, which is 75. So it's going to be 75 multiplied by what? The distance you cover, which is 10 what? 10 divided by 2, that is half of the distance, that is 5. All right, but don't forget again, we still have this moment here, and it is what? Negative. So we are going to have minus 282.5, which is going to give us, if we do this math, we are going to have our bend moment at point D to be equals to nothing but what? Nothing but 137.5 kilonewton. 137.5 kilonewton meter. All right, so that is what we are going to have. All right, so now the next one is the bend moment at point C. All right, now I want to show us something here. All right, you can, we said our bending moments, from the definition of bending moments, is either you say the sum of moments towards the right or towards the left. All right, now when I get here, for the purpose of being fast, you understand, as I stand here and I know I can take my moment towards this side, I'm correct to do that. I always do that, but I want to show you something again. Instead of me taking the moment towards this side, I can stand here and I take the moment towards this side. It is still the same answer, because we know that clockwise moment is equals to what? Anti-clockwise moment. All right, this one is basic from our physics, right? All right, so if we stand at this point, we can take our moment towards this side. It is much easier to do it towards this side than coming from this side. All right, because of the load, the moment, and the distance that we have. All right, so it's better I stand there and I just do it, but I can still do it the other way around. All right, so now if we stand at this point, now we are going to have this upward force, so now which is going to multiply 5. All right, so that is ROA. What is our ROA? Our ROA is 115.5 multiplied by what? 5. All right, so, and don't forget, if you stand at this point, this one here is going to be giving us a what? It's going to be giving us a what? A clockwise moment, right? Why this one remain what? Anti-clockwise. So this one will be negative, why this one is giving us a clockwise moment. So we are still going to have minus 417.5. So if you do your math, we are going to have our bend moment at point C to be equals to nothing but what? Nothing but 160 kilonewton. All right, so that is what we are going to have. All right, so now the next thing we are going to consider is the bend moment at point what? At point A. All right. All right, so the bending moment at point A, the only moment that we have at point A is just this moment that is here. If we have a simple supported beam on a normal day, we are supposed to have a 0 here, right? All right, so now, but the only moment that we are going to have is just this moment that is here. Oh, sorry, I might be wrong. All right, if we stand at this point, it's a simple supported beam. You can take your moment towards this side. From this side, take your moment towards this side. Is that clear? All right, so but instead of me doing that, I know it's a total waste of time. I can stand here and take the moment towards this side. Is that clear? All right, just as I explained earlier. All right, so now if I stand at point A and I'm taking my moment towards this side, the only moment I'm going to have is just this moment that is here, which is what? Negative, right? Because I have explained that to us earlier. All right, so we are going to have minus 417.5 kilonewton meter. All right, so that is what we are going to have. All right, so all the information that we need is correct. All right, so now the next thing we are going to be doing is to draw the shear force and the bending moment diagram. All right, so for us to do that, we are going to be starting with the shear force diagram, and this is our reference line for our shear force. This is our reference line for our bending moment. Above this line is positive, below is what? Negative. Sorry, please. All right, and above this line too is positive, below is what? Negative. All right, so let's start with the shear force. So at point B, our shear force is what? 79.5 positive. All right, so let's take this point here to be our what? 79.5, because it is the highest value that we have there. Yes, so let's just take this point here. All right, so that is our 79.5. All right, so don't forget we have a uniform distributed load there, so we'll be using an inclined line. All right, so now at point D, we have our shear force to be what? Our shear force is what? 4.5. all right, so since this, from this point to this one is 75, so it shows that 4.5 should be somewhere around there. All right, so let's join this point. So it's going to be inclined because we have a uniform distributed load there. All right, now our point C, we have our point C to be minus 1125. So point C 1115.5. all right, so let's take this point to be our 111.5. all right, now but again, before we get here, between point D and C we don't have any force, right? So it means that we are going to have a constant line here. All right, so and for the shear for our point C is 1125, so we have assumed here to be our point, and between C and A we don't have any force again, so we are going to have a constant line. All right, all right, so that is what we are going to have. All right, so you can therefore shade now. So we are going to shade all of this stuff here. So we shade, are going to have this, we are going to have this, you have this, you have this. All right, all right, all right. So here we are going to have everything here to be what? Positive. All right, so here we are going to have here to be negative. All right, so that is our shear force. So let's go for our bending moment now. So at point B we have a negative 282.5, negative 282.5. So let's take this point here to be negative 2. Would you also have another negative? Yes, we have two negative there. So we have two negative. So 282 should be somewhere around there. Yeah, since it is around that. Okay, it is not. Okay, so let's take this point here. All right, so that is it. And at point D, we have it to be what? 137.5. all right, so let's take these points to be 137.5. all right, so we are going to be joining this with a curve because we have a uniform distributed load. All right, so we are going to have something like this. All right, so that is what we are going to have. So at this point C now, we are going to have 160. all right, so we are going to have 160, which is higher than this, so we're going to have 160. all right, so we are going to be using an inclined line to join this point together. All right, so and at A we have A to be what? Minus 417, which is higher than what we have here because this one is 28, so I have to take it down. All right, so we use our inclined line to join this point together. All right, That's what we are going to have. So our diagram is going to look like this. So we can shade now. I hope you know why we always shade. Alright, shading is not compulsory. I love it because it will make my work to be very neat. And it will show the true diagram. Alright, so here is positive. Here is negative. Here is negative. Alright. So now that's it. Now let's now consider our point of contraflexure. Alright. So now let's go for point of contraflexure. Alright, so if you look at this diagram well, you see we have our point of contraflexure is also 2 points, because we said our point of contraflexure is the point where our bending moment is equal to 0 as it changes its sign. So now, well, that's fine. This is negative here, this is positive. So this is the point where it starts changing to what? Positive. So this point here is the first point of contraflexure, while this one is the second point of contraflexure, because it changed from positive to negative from this point. All right, so at this point, let's take a line up. All right, so that's it. Oh, sorry, please. All right, so that's it. All right, so what we are going to do is we are going to be calculating the bending moment here. So at this point, let's go from this point to this point. Let's name it to be what? S1. So all right, so let's take this point here to be our S1, and this line that we have here to this point, let's take it to be our S2. All right. All right, so let's start with this point here, because this one is more easier than what we have here. All right, so let's calculate the bending moment that we have here. All right, so if we take the moment towards this side, we are going to have the first bending moment there to be equals to, all right, RA multiplied by what? The total distance, which is what? S1, because we have RA multiplied by S1, then we have this moment here, which is 417.5. So it's going to be negative. So we are going to have minus 417.5. All right. So now, but we know the value of our ROA. Our ROA is what? 115.5. So we are going to have this to be equals to 115.5 S1 minus 417.5. All right, but don't forget that our bending moment, here, we are going to equate this equation to be equals to 0 because of point of contraflexure. Because point of contraflexure is the point where bending moment is equals to what? 0. All right. So if we equate this to be equals to 0, we are going to have 115.5 S1 minus 417.5 to be equals to 0. So if we move that to the other side, 115.5 S1 will be equals to 417.5 rather. So we are going to divide by 115.5, 115.5. This will go with this. Then our S1 will be equals to, so if you divide 417.5 by 115.5, we are going to have our S1 to be equals to 3.6 meter. So it means the point of contraflexure here, it is 3.6 meter from what? From point A. So that's it. Now, let's go for the second point of contraflexure. So let's call this one our S2. All right. So if we call this our S2, then we are going to say the bending moment at that point will be equals to, all right, so if we take our bending moment towards this point here, we are going to have RB multiplied by what? S2. So we are going to have RB multiplied by S2, then minus 282.5, then minus, again, you know, we also have a uniform distributed load here. The weight is 7.5. We are going to convert it to a point load, and multiply by the distance is going to cover, right? So, and it is going to be a minus 2 because it is a downward force. All right, so minus 7.5 S2, we have converted to a point load. Then we are going to multiply by the distance is going to cover, which is S2 divided by 2. I hope you understand this. All right, so and then our ROB here, our ROB is nothing but what? 79.5. So I know we are going to equate this equation to 0. So let's just input the value and equate it to 0. So we are going to have 79.5 S2 minus 282.5 minus 7.5 S2, S2 multiplied by S2, that is S2 square, then all over 2 equals to what? 0. All right, so the next thing we are going to do is we are going to multiply through by 2 here, so that to get our value of S2. But I'm trying to check, maybe I have already input the values here. All right, but I don't think I did that. All right, so if we multiply 79.5 by 2, what are we going to have? But I have my calculator here real quick. All right, 79.5. all right, so that is going to give us a 159. All right, so 159 S2, then minus 282.5. Okay, sorry, 282 multiplied by 2. If you multiply 282 by 2, you are going to have 565. Then if we multiply this by 2, this 2 will cancel out, then we'll be left with minus 7.5 S2 square equals to 0. All right, so we can further rearrange this. If we move this to this other side, if we move everything to the other side, we are going to have 7.5 S2 square minus 159 S2 plus 565 equals to what? 0. All right, so we are going to apply quadratic equation here. So it shows that S2 will be equals to, from quadratic equation, minus b plus or minus root b square minus 4ac divided by 2a. All right, this is our a, this is our b, this is our c. So we are going to have minus 159 plus or minus root b square, which is minus 159 all square plus 4 ac, that is multiplied by 7.5 multiplied by 565, then divided by what? Divided by 2 multiplied by 7.5. all right, so S2 will be equals to, all right, so here we are going to have this to be 159 plus or minus. By the time you do your math here, you take the square of this, then you multiply this together and you add the result, you take the square root. You are going to have this to be what? 91.27 divided by 2 times this, that is 15. All right, so now for you to get the correct value of our S2, you are not going to take the positive sign, because by the time you have divided that, I hope you are going to be getting 16 point something. All right, so 16 point something cannot fall between this distance, so you are going to neglect that. So you are going to be going for 159 minus 91.27, then you divide the result by 15. Our S2 there will be equals to 4.51 meter. All right, so this will be the correct solution to the second point of contra-flexure. I believe you understand this. So this is how to go about this solution. Thank you so much. Peace out. And don't forget to subscribe to our channel and